I'm Edmund Hunt, postdoctoral fellow at the University of Bristol. Very happy to be here at this virtual Alife conference to talk about my work with Nigel Franks and Roland Baddeley, entitled The Bayesian Superorganism, Collective Probability Estimation in Swarm Systems. So this paper is actually part 3 of a trilogy. You can see the other 2, they've been published in Royal Society Interface. They were looking at Markov chain Monte Carlo methods as models of movement. This paper is looking at collective animal behaviour for probability estimation for the purpose of collective decision making. So the title, The Bayesian Superorganism, which somebody suggested would be a good name for a metal band. I'll explain what these 2 terms mean. So the superorganism concept refers to things like ants and honeybees and termites, which, even though there are lots of individuals, up to hundreds of thousands of individuals, they actually work together biologically more like a single organism with common goals between these individuals. And by studying them, we can witness the emergence of a higher level of biological organization, things like collective decision-making capabilities, which are just incredible to watch. And because their societies are so tight-knit, we can actually observe extraordinary cooperative adaptations. And in fact, we would even anticipate them to have special abilities for doing things like estimating probabilities. So that's where we begin looking at the ants. We look, for our superorganism, at house-hunting rock ants. They're our model system. Not all social insects build their nests from scratch. Some actually go looking for one in pre-formed cavities, in our case in little rock crevices. Temnothorax albipennis ants are continually monitoring their environment, looking for better nests. And they actually have to do this very well because their nests crumble easily. They're fragile rock crevices. And they've got consistent preferences for what they like in a nest. They want it to be a certain size, to have a certain brightness level. And we can manipulate the options in terms of those preferences and watch how they can weigh up the options if different quality nests are available. So that makes them a model system for collective decision making. And this is what I mean. You can make an artificial nest by taking a little cardboard perimeter with an entrance in it and sandwiching it between 2 microscope slides, and you can manipulate the qualities. So that's an example of a poor nest, doesn't have an entrance, doesn't have a roof, all the way through to an excellent nest which has, the right height, a nice little defensible entrance and a dark lid on the top of it, which they prefer. So we can perform these nest choice experiments. You take the lid off, you destroy their nest, and then they can solve this collective decision-making problem, which is often referred to as the best of n problem. So they can choose between 2 options, 3, 4, 5. They can solve the problem of finding the best option, even when there's lots of options, in this case 5 options in this picture. So how do they do that? So the other part of the title is the Bayesian part. So I'm sure many of you are familiar with the idea of Bayesian statistics. Bayes' rule is shown here, whereby you think about probabilities more in the sense of degrees of belief or confidence in your assessment of the state of the world. So if you're an ant and there's 2 options, for example, if you've not seen them, you might assume that there's an equal chance that they're good. Those would be called your priors, and you might say that there's 50% probability attached to each one of them. But then as you make assessments, you get evidence, and then you've got to integrate that evidence with these prior probabilities to obtain what's called the posterior probability, the updated probability. And we're suggesting that, what ants will need to do then is make observations and update their assessment of which option is best according to Bayes' rule. And really the main kind of thesis of the paper is that Bayesian statistics can not only be seen as a tool to sort of describe how individual animals must be updating their beliefs, but actually as a model of real-world physical behavior, as a physical realization of Bayesian inference. So as the ants move around, that kind of corresponds mechanistically to a realization of this process of Bayesian inference. That's sort of our thesis, if you follow me. So the question then is it feasible for an individual ant to kind of compute probabilities and get the kind of the full solution to the best of n problem? What it would need to do is carefully inspect each option and then use behavioral somehow, which requires this likelihood function in behavioral, which can be quite hard to obtain, and figure out the probabilities of which one is best. But this perhaps isn't feasible, right? Because it would take too much time, it would take too much energy, it would take too much brain power, it would require maybe a lot of communication between ants to make this work. So instead, what we're suggesting is that if the individual ants look at 2 or 3 options and kind of decide, well, this one's good enough, I'm going to accept this as a decent option, that will still allow them collectively to make a decision. And this process of accepting or rejecting options, we're going to map onto this process called approximate Bayesian computation. So it's kind of hard to explain approximate Bayesian computation in a minute or two, but this is a very helpful diagram from this paper from Sunaker et al. Say the ants have made some observations. They want to relate these observations to, well, what is the true state of the world that is generating those observations? And that kind of would correspond to saying, like, well, we've got some data and we'd like to understand what is the model that is potentially generating those statistical observations, right? And in a model, say you've got a normal distribution, that's described by a mean and a standard deviation. You would want to estimate those parameters to estimate what is the model generating the data. And you can do that using approximate Bayesian computation. So what you would say is you would start with a prior distribution on that parameter, say it's the standard deviation, theta in this diagram. You start with a uniform distribution, then you would draw samples from that distribution, and then you would generate some simulated data given that parameter sample. You would then compare that simulated data set to the data you've actually got. So in this case, you can use something like the mean. So you see in the top left, the red curve, that's summarized by this mean mu. You can compute that mu for your simulated data from your simulated parameters, compare it to your observed data, and see if it compares sufficiently well according to this epsilon criterion, whether they're sufficiently close together. So in this case, in the diagram, you're rejecting simulation 1, rejecting simulation 3, but accepting simulation 2 and, well, n it's called there. And that gives you your posterior distribution, and you note that you didn't need to use a likelihood function anywhere along there. And what we're saying is by the ants making observations and accept or reject decisions, that essentially corresponds to this process of approximate Bayesian computation, whereby the final positions of all of the ants corresponds to the posterior estimate that each of the available options is in fact the best one. All right? So to give you an example of what this could look like, you've got 5 ants here, and they're making a few observations according to some sampling rule. In the paper you'll read about, I'm saying they could be doing something called Thompson sampling, but they could do it some other way. But let's say the ants start with identical priors for each of 3 options. So let's say it's a probability of a third attached to each one being the best. That's described by this horizontal line, the dotted line in the diagram. But then the true qualities are shown by the bars. So what they need to discover is that, in fact, option 3 is the best one. So if they make some observations, they move around a bit, and then they say, well, this is the one I think is the best. That's their own individual independent decision. What's happened here is that 4 of them are on option 3, 4 out of 5. So what we're saying is that that actually corresponds to an 80% probability that it is the best one. And it's as simple as that. The macroscopic distribution in terms of physical positions corresponds to the probability distribution. Okay, that's pretty much it. That's the main thesis of the paper. So this is a simulation of ants doing that, making independent sampling decisions and moving around to which one they think is best. Here we're saying location 3 has got a quality of 1.2, so it is the best one. And you see after a period of time, 8 out of 10 ants are at option 3, so we'd say they've come up with an 80% probability that that's the best one. Okay. However, there might be some challenges to this, right? They might prematurely settle on an option that is what they think is good enough, right? And inadvertently miss what is in fact the best option. Okay, so what's happened in this diagram is some of the ants have looked around and they've settled on the medium quality option. And as a result, they've said, oh, there's an 80% probability that option 1 is the best, but that's rather inaccurate. Okay, so how can they deal with this problem of premature convergence? Well, what they can do is this rather charming behavior called tandem running. So here's a video, and if an ant in real world biology finds a good option, what she will do is she will go back to the starting point, to the original nest, and lead one of her nestmates to that point to say, come and have a look at this. It's worth making an assessment of this option because I think it's really good. And so this other ant, the follower ant, will follow the leader ant to this good option. Okay, and what you would hope to see is that as a result, more ants accumulate more quickly at that location, and that's how they make a collective decision, is enough of them, a quorum threshold of ants has arrived at the good option. And we're saying, well, you can map that to these Bayesian methods by recognizing that it's akin to this technique of particle filtering, which is a form of importance sampling, which again effectively says if you find a good part of the probability distribution, it's worth sampling again, preferentially from that high probability part of the distribution. So in this case, we're saying one of the ants has exceeded a threshold. If they find a high probability that they think this is a good option, they will then go and recruit another ant at a different location to say, come and have a look at this option. And you see what's happened here as a result is that the posterior probability has been boosted at option 3, and as a result they've obtained a more accurate estimate that indeed that is the best option. Okay, so again, this is the simulation I showed you before. This is the macroscopic distribution of the 10 ants, and you see they reach this 80% mark much more quickly. At around 20 seconds, they even get up to 10 ants at one point. So we're saying this tandem running behavior is like particle filtering, and this helps to explain this mechanism that they've evolved. So to conclude, we're saying superorganisms flourish because they've got these fantastic collective information processing capabilities, and we can use a Bayesian framework to describe and explain what they're doing in informational terms. We're suggesting that their collective cognition can be described through this spatial approximate Bayesian computation. And in future work, what we're hoping to do is demonstrate this in robot swarms, so it could be used in other collective systems. So thank you for listening, and I'd be really happy to take some questions. Do shoot me an email or follow me on Twitter if you want. We can continue the conversation. All right, thank you.